Since we are using dynamic programming, the first thing we look for is some optimal similar substructure. Recall that the key realization in understanding the single-source shortest path algorithms, like Dijkstra and Bellman-Ford, was that subpaths of shortest paths are shortest paths. So if this is a shortest path between uv, and it happens to go between x and y, then this subpath must be a shortest path between x and y. If there were a shorter one, then it could replace this subpath in the path from u to v, and that would then give us a shorter path from u to v. This type of argument is called cut and paste for obvious reasons. By the way, throughout I'll use squiggly lines to indicate the path between two vertices and straight ones to indicate a single edge. Unfortunately, by itself, this substructure is not enough. Sure, we might be able to argue that a shortest path from u to v must take a shortest path from u to a neighbor of v first. But how do we find these shortest paths? The subproblems end up having circular dependencies. One idea is to include the notion of path length defined by the number of edges used. If we knew all shortest path that only used k-1 edges, then by examining the neighbors of v, we could figure out the shortest path with k edges to v. We'll let delta uv of k be the weight of the shortest path that uses at most k edges. Then the recurrence is that delta uvk is the minimum of delta uvk-1. This is where we don't use that potential kth edge. Or it's the minimum of the distances from u to one of the neighbors of v, using only k-1 edges, plus the weight of that last edge to get us to v. This strategy works, and it yields the matrix multiplication shortest path algorithm that runs in time v cubed log v. See Corman, Lyerson, Rivest, Stein for details. We're going to take a different approach that will yield a slightly faster algorithm and allow us to remove this log factor. We're going to recurse on the set of potential intermediate vertices used in the shortest paths. Without loss of generality, we'll assume that the vertices are 1 through n for the convenience of notation. Consider the last step of the algorithm, where we have allowed vertices 1 through n to be intermediate vertices, and just now we're considering the effect of allowing n to be an intermediate vertex. Clearly our choice is either using the old path, or taking the shortest path from u to n, and then from n to v. In fact, this is the choice not just for n, but for any k between 1 and n. To get from u to v using only intermediate vertices 1 through k, we can either use k by taking these shortest paths, or not use it. Therefore, we define delta uv of k to be the minimum weight of a path from u to v using only 1 through k as the intermediate vertices. Then the recurrence becomes delta uv of k is the minimum of delta uvk-1, that is, not using k as an intermediate vertex, and using k, that is, taking the shortest allowed path to k from u, and then going as quickly as possible from k to v. In the base case, where no intermediate vertices are allowed, the weights and the edges provide all the needed information.